So yesterday we talked about discriminative models, which allow us to use labeled data that for which we understand the pair of a data versus the class that it belongs to. We understand that pair, and we can use that information with that annotation to do supervised learning and perform a variety of tasks that we saw yesterday. The transition to the 2 lectures on generative models happens today, and the delineation is between the topic that I'm going to take up today, which is exploring patterns in data. So just to be clear, we only have the data without understanding what classes it belongs to. But still, all hope is not lost. We can just by itself look at the data and understand, ask some questions and find some patterns. Tomorrow, we'll continue down the path of, what's that? Monday, yes. Tomorrow you'll have a well-deserved break. We all do. And then on Monday, we'll talk about the topic of, again, having unlabeled data, but using it in the sense of trying to find the underlying distributions and then generating new data from it. So that's the distinction between these two. So let me move on and tell you what the outline is. So the outline of today is, first we're going to talk about that has the flavor of finding dispersions, structures that have the form of dispersions in the data, the directions of dispersion. That's the first one. And also use that in terms of dimension reduction. Yesterday, Enrico talked about surrogate models, models that are computationally reduced, and you can run in place of highly computationally demanding numerical models that use, for example, finite difference, finite element spectral methods. And so the whole idea of finding a reduced space is related to the first topic I'm going to talk about. The next 2 topics have to do with clustering. And related to that is the task of segmentation. I'll go in details, but the idea there again is your data is not random. It typically resides in some space that clusters around perhaps spatial or temporal dimensions. And the idea is that how do we find those clusters? And the 2 topics in particular that I'm going to talk about under that, starting with the most intuitive one, which is k-means. It's already been discussed. Some of you have looked at it. And then just generalize that in the same spirit of starting with something that's intuitive, but then showing that that's only a special case of something known as a Gaussian mixture model. And if I have enough time, I might talk about generalizations of the type of optimizations that are needed for these types of problems, k-means and Gaussian mixture model, and a broader class of problems that require alternating optimization. Okay, so again, I've placed just one reference, but there are many. So as a reminder, what we did yesterday under supervised learning, we built these discriminative models, and the idea was we have a data set D of some dimension that has these pairs of data, xi's, or samples, and the corresponding classes. We started with binary, and then we generalized it to any arbitrary number of classes. And the general idea was that slowly we started with very simple mappings, that were linear, first with linear regression, then we talked about logistic regression, and then eventually we generalized to the case where we had broad, unconstrained, nonlinear functions captured by essentially an activation function and a layered perceptron, which means a combination of an affine functions and composite functions that enabled us to be able to do universal function approximation. And then Enrico talked about that a little bit in the context of illustrating how you can essentially use 2 odd functions to build an even function. Okay? by just adding terms. Okay, so these were the 4 topics that we talked about. But of course, there are many. And by the way, there are many topics that we just don't have time to talk about. There's a whole host of statistical techniques, for example, known as boosting. Some of you may have come across. The idea there is that everything that we are talking about here is just building an inference engine, a predictor, a predictive model. But then if you have the quality of that prediction is not good, right? You have what is known as a weak learner, but then you have multiple of those. So for example, multiple techniques for doing the learning. How do you combine them? So that idea is also has its own line of literature and development, but we're not going to get to that. But I'm mentioning it because it's useful for you to read. If you come across it, understand the compartmentalization of where that resides. Okay, but today we're going to come into the scenario where we just have data, okay, samples. And presumably these samples come from some underlying distribution to which we have no access. So what are the goals of this unsupervised learning? Is to recover hidden structure. And I'll talk a little bit more about that because we have to specify what we mean by structure. Structure is just a catch-all word, right? Of course, as I mentioned already, these are used for data compression or dimensionality reduction. We can explore or explain data. So this whole idea of exploratory and explanatory. What do I mean by that? If we look at some data and we can understand what clusters it may belong to or how many clusters there are, or for example, where is the largest dispersion, in what direction, among which one of the physical variables we have the largest dispersion, then that may allow us to say something about the underlying governing physics that generates that dispersion. And also, this I alluded to yesterday, we can construct features for supervised learning, because now if I can essentially come up with a generative model, an underlying model that allows me to uncover structure in it, then perhaps that will give me a way to now generate some labeled data. If I know what clusters that data belongs to, so I already have some notion of which classes a particular data belongs to, and so I can generate essentially synthetic supervised or labeled data, annotated data. So those are all different ways that we can think about what the objectives are and what this framework would allow us to do. Okay, why modeling a distribution? I have already spoken about this. Synthesis of objects, that's the generative part of it that we're going to focus on Monday. And there are other areas. There are other areas that have to do with essentially simulating an environment. So there's an area, another topic, very important topic, on which dedicated courses and textbooks exist, known as reinforcement learning. And that has to do with the notion of not just learning, but also translating what we learn in an environment into actions, decisions and actions in real time. So there's a notion of a dynamic decision making. And so all of these will enable some of those tasks. And I already talked about leveraging on labeled data. The 3 topics that you see here listed on top are the topics of Monday's lecture. So we'll start with variational autoencoders. And the idea here is essentially if we know that there is a pattern in a high dimensional data that resides in a lower dimensional space to which we have no access, perhaps we can introduce an auxiliary or a latent space variable that can find where that information in a lower dimension resides. And so that's what the idea behind the first development here is. The next idea is to actually, based on some concepts from game theory, to directly learn the underlying distribution by essentially playing a game between 2 elements. By these elements, I mean elements that have building blocks using the deep nets that we talked about. One tries to synthesize data and show synthetic data, and the other element tries to figure out if it's synthetic or it's from the training data, the actual X data that we have for the samples. I'll talk about a topic that's more of an emerging topic. It's I would say, quite active. That has to do with essentially score-based generative models or diffusion models. I'll talk about that toward the end of Monday. Today, these are the three topics, as I mentioned, that we're going to talk about. Okay, so let's set up the framework. We, of course, started with maximum likelihood. And just as a reminder, in words, conceptually, we build a likelihood function, and we want to maximize that. And similarly, we can minimize negative log of that, and that's been the pattern that we have followed for all of the developments. So what's the general model? It's a conditional density. That's what we call a likelihood function. The probability of the class, this y is a vector of discrete elements, a set of discrete numbers, given the data. And this is what I mean by negative log likelihood. We write it in terms of this exponential of some nonlinear function with some perhaps what I refer to as a temperature parameter, so that we can generalize and abstract what particular cost this model, this function f, belongs to. It's a function of, as we've seen from early on all the way, from very simple regression all the way to deep nets. So it's a function of the class, the data, and the corresponding weights for which we solve an optimization problem for the best matching to the desired function. And there's a normalization. This is just in the bottom. You're just normalizing, and we've had that normalization factor. And again, I already said this in words. Y is discrete output space. X is input space. And now, what do we do if there's no Y in this expression? So I'm going to just say that now we don't have Y anymore. We don't have the classes. Well, here's one formulation. Given data points X, how can we model the distribution of X, the probability of where that X was drawn from? So the maximum likelihood approach in this case takes a slightly different form. It's really a parameterization. So instead of the weights that we had, the weights for which we were minimizing some residual cost between the labeled input and the classes, now we are optimizing, again, for a parametric form of a representation. So, for example, I'll tell you very specifically. So we want to find a set of parameters, maximize that parameter vector. For Gaussian, it's just a two-parameter vector, right? It's the mean and the variance. Again, log of that likelihood function. That likelihood function is just a parameterized density. A Gaussian with the two parameters. That's what we're talking about, okay? So the simplest example, as I've said in words, is to fit mean and variance, the two parameters of a Gaussian distribution. What does this imply? This implies that we are assuming a priori that our distribution is that the data, the distribution, the probability of X is distributed according to a normal distribution, but we don't know the spread, the dispersion, or where the center resides. That's just one example. Okay, fit parameters theta of a mixture distributions. For example, a mixture of Gaussians. So instead of just one Gaussian, I have a distribution that's more complex, right? Gaussian is nice and it's common, but a lot of distribution, as we've talked throughout this week, is a mixture of those. So you can, with a mixture of Gaussians, you can get arbitrary shapes for a distribution, right? Depending on how many Gaussians you have, each one of them is at a different sensor with a dispersion and with a different amplitude. Okay, so it's a generalization for being able to capture more complex arbitrary types of distributions. So this, by the way, it's not, I'm saying it in words, but we can visualize it easily, right? Because suppose we're talking about two mixtures. That means that you're drawing samples from two Gaussians, but the Gaussians are apart in where the center of those Gaussians are. And the dispersion could be different. That means you have a cloud, a cluster in one place, and the data comes from somewhere else, and you really want to figure out, is that how it is, or is it just one Gaussian? So that's an example. Okay, so let's go into some specifics And this is important conceptual point that you need to make sure that you fully understand. The likelihood in the context of, for example, linear regression or more broadly discriminative models is a conditional probability, a conditional density, conditional distribution of the classes given the data, okay? And so for a Gaussian, remember, this is how we started talking about linear regression. You have a Gaussian distribution where the mean of that Gaussian is just like that line, is the product of the weights times the functions of the data, right? This is the mean of the Gaussian that we are centering. Okay, but in a generative form, we don't have y, so this y will disappear from this formulation. What do we have? We have the likelihood changes form, it becomes probability of the data given which mean and which variance. So you have some data, and now your likelihood function is, well, if I am given some mean and variance, what is the probability that a particular data X will be generated from that particular sample Gaussian? So think about a whole range of different Gaussians that's possible. So what the likelihood in this case, the form that it takes, it's again, it's a conditional density, but it's conditioned over the parameters of a model for which this random variable xi's are being drawn. Okay, is that clear? Because that's at the heart of everything. Okay, so now let's look at the form of the expression. What changes? What changes is that I just have the standard form, in this case, just a Gaussian random variable, xi, individual Gaussian random variable, subtracted by a mean and with the corresponding variance, the dispersion. Okay. So what we are really interested in here is modeling the distribution of the data xi and not the class labels. Right? That disappears from this formulation. Okay, let's talk about it a bit more broadly. Again, remember, we have now, in this case, I'm writing it instead of just the conditional likelihood. It's just the probability of the data points, the samples that we have xi, parameterized by a parameter vector theta. You change theta, you get a different distribution. So that's essentially is parameterized by theta. And we're looking at the log of that. So we're looking at the log of the probability of xi over what I will refer for the first time. This will come up a lot on Monday. And people have referred to it and mentioned it already. This vector z, which is typically referred to as an auxiliary or a latent variable. What does it mean? Let's make it concrete. I have no access ahead of time to what the mean and the dispersion of that Gaussian is. I cannot observe it. So latent variable means that you have no access to it, but nonetheless, that's what plays a role in this parameterized density function, okay? And so the task is, can we learn that implicitly, that latent space in this formulation? And of course, this is going to get a little bit more sophisticated when we talk about variational autoencoders and other developments on Monday. In a discriminative formulation, it was actually a conditional density, but the parameterization was based on the weights, the arbitrary weights that eventually we came up with in terms of a set of weights as inputs to activation functions for a deep net, the output of which becomes weights to the next layer and the bias. Basically, we had the bias and the weights that gives us an affine linear function, and the composition of those in terms of essentially input of one layer going to the output of the next. Okay, so I've already described this. Z is the latent variable. It's never observed. And in the discriminative model case, Y always completely observed. So let's talk about, in fact, before I talk about this, let me go back and close the loop on something that I mentioned, and that's the notion of structure. So this is the setup, the framework, but our interest is to find structures in data, just data that's not annotated. There's no label. We don't know what class it belongs to. First of all, what do we mean by structure? Let's start there. We all have a feel for what, in fact, we use it, everybody. Oh, structured data. Oh, there's structure in my data, but what does it mean? Moments, okay, what does that mean? Okay, if I have data, I can compute its sample average, right? But what is that, what does that tell me about structure? Okay, very good. Okay, so that's good. So that's a very concrete example of the amount of spread of data and where it's concentrated that has some notion of the structure. Some data is clustered in a very narrow fashion, others may be dispersed. And the next is that, for example, if in the simplest case where you have some scattered data points, like I showed you in the previous example, and that scatter is not necessarily around the circle with a center, right? There's a dispersion, and so one question could be, I want to understand where the highest, what's the direction of the highest dispersion in my data? That already is something that is better than nothing, right? We can actually, so this is without having any label that has a lot of information. So in a high dimensional space, I want to find out, for example, it could be a plane now we're talking about 3D. What are the vectors that make that plane that give me the highest dispersion in a 3D scattered data set? And when you go to higher dimensions, this becomes also harder to, of course, very hard, impossible to visualize, but that's a very important tool. So when you have multivariate data sets and you're trying to figure out under which one of those, the multivariate data set could be capturing a multidimensional set of physical parameters in an environment, and where is the direction of the highest dispersion. So that's a very useful information. That's an example of what we mean by structure. There's a simpler notion of structure, but I'm not going to talk about this because you all know about it. For example, pattern. What do we mean by pattern? Let's start there. The ideas about. Again, pattern is one of those things that we all have a feel for, but yes. Simpler characteristics than what? Thank you. Similar characteristics. That's good. So similar meaning similar to, let's say the simplest case, a data time series, data set, and you're saying that parts of it are similar to other parts. That's what you're talking about, right? Yeah, and that's the notion of a periodic structure. So that's the simplest form of a pattern, right? Basically, you have a periodic time series with some period, it repeats itself, so that's the simplest form of a pattern. It's a repeating pattern. It doesn't have to be, not all patterns have to be repeating. That's an important realization. But the simplest form is what essentially the reason why we do harmonic analysis, we look at Fourier transforms, we look at power spectrum, is because the hope is that there is an underlying periodic structure that makes up this time series. And so we can do harmonic analysis on it. But patterns don't have to be periodic, right? For example, for let's say a chessboard, okay? There are experiments that go back to a long time ago. If you just stop a game, a chess game in the middle, and to someone who is a chess master or trained, then do you reconstruct that pattern and how they remember it versus just some random pattern that doesn't belong to a game that's ever been played, but just random placement? The distinction is known to someone who has an expertise in terms of having looked at things that are actually feasible from a game or a random placement. So, I mean, what does not have a pattern is essentially this white noise that we're talking about, right? Apart from that, you can always think of things as having some hidden patterns in them. So the first thing that I want to talk about is the notion of that structure being captured by the direction of dispersion. Okay, so that's the first. And so what's the problem? Let's define it and be more specific. So I'm showing you a scatter plot, right? This is in 2D. This is the data that I'm drawing. And of course, when you look at this visually, because we can visualize it easily here, if I ask you what's the direction, give me the vector that gives the highest dispersion, it's easy to see that that's given by this light blue in this direction. That's the direction of highest dispersion, right? Now, if I ask you again, give me the second vector that two conditions. First of all, is orthogonal or perpendicular to the first vector, and also has the next highest dispersion. Again, that's not difficult for you to visually tell me that, yes, it's in this direction, with that small vector. But what happens when you go to high dimensional space, n-dimensional? That's not an easy thing to answer, and that really is the objective here, to develop a framework for which we can actually answer this. In other words, find that pattern of successive directions that maximize dispersion that are orthogonal to each other. And the orthogonality, does anyone know why that is desirable in this context? It's related to one of the topics, huh? Yes, and so essentially what that allows us to do is to be able to use those, essentially the orthogonal directions, to combine and go in reverse. Only if we have maybe a few of those directions with a reduced number of representations. It's essentially a transformation, right, into these new coordinates. And with that transformation, what we can do is that with a reduced number of all the variabilities that exist in the original data, much less than the dimension of the original data, reconstruct in an approximate fashion that original data. This is the idea referred to as dimension reduction, which is the basis of, for example, surrogate models. The reason that, or many other things when we talk about variational autoencoders, why we are able to represent a high dimensional data in a low dimensional space, okay? Because most information and patterns and structures reside in a lower dimensional space. Okay, so this is referred to as principal component analysis. It has other terminologies referring to the same, more or less the same idea. For example, this X-centered data with respect to a set of parameters. I want to basically do a linear projection of, that means this W transpose time X. I want to find these W's, the projection, the direction in which I project the data, for which this variance is maximized. And so there's another constraint here, is that I want those weights to essentially be normal, right? So you add up all the weights, that basically becomes 1. W transpose W is 1. Okay. The next thing I do is I expand the argument of the variance. What do I mean by expand? I mean basically write it in terms of this inner product. So W transpose X bar, right, times, just like this. All I'm saying is that write it in this form, okay? The definition of what the variance is this is expected value. You already said that. It's the expected value of W transpose X bar transpose W, okay? And we already know that, I already talked about the sample mean, but what is this quantity X bar transpose in the center? Sample variance. It's just basically, again, it's not the variance of the distribution because we have no access to the distribution, but whatever sample data we have, we can build a sample variance, or sometimes it's referred to as an empirical variance. And I'm going to denote that by this sigma over here in the middle, okay? So now my maximization problem, because I want to maximize W transpose sigma W with the constraint that I'm normalizing W. Okay. The norm of W is 1. Okay. So that's, so now, just to be clear, what I'm interested in, what I want to solve for is the W. I want to find a W that maximizes this product, W transpose sigma W. Okay. Yes? So it depends on what you mean by help. So you said, would it help in any way? And the answer is that you certainly can use L1 norm, L infinity norm, any arbitrary P norm. You can do that, but the reason I'm using L1 norm is because I'm interested in maximizing variance. And variance is defined in the Euclidean distance, right? If there are other attributes you want to, what you call structure, if it's not dispersion, if it's something else, if it's a higher order moment, kurtosis, or whatever it is, you can define it that way. Yeah. Okay, so the question now is, how do we solve this maximization problem? And in fact, let me go back before I gave you the solution. Remember what I'm talking about. I want to maximize this quantity, but I have a side constraint. So I cannot use, you remember when I talked about gradient descent as a numerical way of solving an optimization problem, that corresponds to an unconstrained optimization problem. But if we have side constraints, there are other things we have to do. In fact, take a course in optimization, half of the course is spent on constrained optimization, starting with, for example, projections, talking about what I'm going to show you, Lagrange multipliers, method of those things, and then more sophisticated approaches. But all we have to do is essentially, I'm going to remind you, this is really from multivariate calculus. It doesn't even require a formal treatment from optimization theory. So how do we do this? As a reminder, I want to write a Lagrangian, and the Lagrangian is the constraint here. What's the constraint? The constraint is that the norm of W, which is what? W transpose W, that's the norm, is equal to 1, okay? And I always, for a Lagrangian, I want to make sure that the constraint is on one side and 0 on the other side. So basically what this means, if I were to translate this into the form of a Lagrangian, W transpose W minus 1 is equal to 0. And then what do I do? Here, I have it over here. I have a lambda. And typically, when you build a Lagrangian, this is a plus. Anybody know why it's minus here? Well, usually when you talk about Lagrangians, you're talking about minimizing a function. Here, I'm maximizing a function. That's the only thing. Okay, it's just trying to give a little bit of mental simulation since it's early morning on a Saturday. Okay, and what's the rest? Okay, I add these things together. That's my Lagrangian, and then what do? I essentially take the derivative of this Lagrangian function and set it to 0. And if I do that, it's just an algebra. And with that algebra, some terms cancel. I end up with the following relationship. What is this relationship? Variance, covariance times, this is a covariance matrix, times the vector of weights is equal to this lambda, which is the Lagrangian constant, times that vector of weights. Does this look familiar to anyone, apart from the fact that it actually has a label next to it? Okay, so what's the significance of this? Well, we all know what an eigenvalue, eigenvector problem is. At least we know what it does, but maybe it's useful to think about it a bit more conceptually. First of all, just by looking at the expression, what is it that I'm doing? I am converting a matrix multiplication, matrix times vector, into a scalar multiplication. Scalar times the vector instead of a matrix times the vector. So it allows me to eliminate that matrix vector operation, right? And by the way, some of you already have thought about it this way, but it's no surprise that this, you can think of it as a generalization of what I talked about 2 days ago about the convolution theorem, the fact that the convolution, if you think of it in terms of a transformation into the Fourier space, now your operation of convolution becomes, the cumbersome operation becomes just multiplication, right? And that multiplication, by what? By Fourier series or Fourier transform coefficients, one at a time. Scalar, so you only wait because of these complex exponentials, you just change the value of these complex exponentials, the amplitude and the phase, and you add them together, right? So it's exactly, this is a generalization of that same concept. Okay, that's fine, but what is this, what sort of transformation are we talking about? It is a transformation, right? In other words, I want to be able to operate not this matrix vector multiplication, but just one coefficient at a time. So I have to perform an eigenvalue, eigenvector decomposition, right? What does that decomposition in terms of a geometric interpretation, what does it do to me? I'm working in the original coordinate. Just always think about just like a two-dimensional space, right? And now I'm transforming that coordinate so that I don't have to multiply things by just basic, or vectors, but scalars. So what do I do to that original coordinate? Yeah, I can see the hand gestures, that's correct. So it's a transformation, coordinate transformation, but it's one in which the magnitude is preserved. So it's essentially an orthonormal rotation. Okay. Now, that orthonormal rotation, what it gives me, you can think of it in 3D. Basically, now I'm in a new space in which the magnitudes are preserved, and all I have to do to build any three-dimensional vector is just multiply each unit vector by that corresponding eigenvalue. So it becomes simple, right? And of course, I can go back to that original vector. The reason why I'm slowing down and lingering on this is because, well, I'm going to show you how it plays into the question of interest to us, maximizing the variance. That is going to be important, that conceptual understanding of how we do dimension reduction. Yes? That's a good question. The answer resides in the fact that, first of all, I don't have to reconstruct. Once I have done the decomposition in the new coordinate system, because of the fact that I'm looking for the directions of maximum variance, perhaps with just 3 vectors or a handful of vectors much smaller than the data dimension, I can capture most of the information in the original representation of that distribution, which would allow me to now, with a subset of that representation, maybe a handful of eigenvalues and eigenvectors, come up with a very close approximation that captures most of the information in the region. This is, by the way, I'm going to show you an example of what's known as eigenfaces. I'll show you, for example, for face recognition. That's an example. Okay. All right. So the question is, which eigenvalue, eigenvector? We know that it's an eigenvector, eigenvalue problem. Should we take? Remember, we want to maximize this variance with respect to the weights, and of course, because this sigma, we know it's diagonal, right? So there are these lambda i's, like lambda, or if you look at just one vector, there's a lambda for that corresponding vector. And so I can move it outside of the matrix, so lambda times W transpose W, which, remember, W by constraint that we had right here, this constraint, these are orthogonal, right? And orthonormal, which means that this product is 1, so it's lambda. So the quantity that I need to maximize is the eigenvalue. Well, that is all very nice because we know when we do eigenvalue, eigenvector decomposition, I order them from the largest eigenvalue and down. So all this means is that do an eigenvalue, so I'll say it in words. I have a data set, all these X records. I do a eigenvalue, eigenvector decomposition of that data set after I've centered it. And then I want to find out the direction of maximum variance. That direction is given by the eigenvector that corresponds to the largest eigenvalue. So that's what we're talking about. Okay. What does that mean? It means that if I do that decomposition, here, this light blue line is the vector that corresponds to the direction of it's the direction given by the eigenvector that corresponds to the largest lambda eigenvalue, okay? And then here is the second and so forth. So the question the obvious question, what if we want to find the direction with second, third, and so forth? Largest variance that's orthogonal to the first and second, like the third one. Well, as you can imagine, it doesn't change anything because we've already done our decomposition. Eigenvalues are ordered. So basically, we just go through successive operations as before. So what does that mean? It corresponds essentially to finding that d-dimensional subspace that captures the largest variance. So we want to basically maximize not just one set of weights, but d weights, W1, W2, all the way to WD, where these W's are orthogonal or orthonormal to each other, right? Each one of those vectors. And we can write it as maximization of now a sum, instead of just that the vector, a sum over d vectors, the product that I had before, the same product. So the algorithm is just to work sequentially one vector at a time and compute a matrix eigenvalue decomposition. Okay, so in other words, I can go in one dimension, in the other dimension, and then finally the dimension that we can't see where the scatter comes. And you can just do this successively. Okay, so how do I write it? Collect all subspace directions. These are the vectors of weights I want to solve for, right? And write it in matrix U. So this is W1 all the way to WD. Project points into the subspace. This is the compressed space. And that projection means I have this new x hat, which is U transpose times the centered version, x minus mu. Okay, now I want to go back. I want to just use these, essentially these, after the transformation, I have these coefficients, right? Expansion coefficients is what's usually referred to. I have these expansion coefficients. I want to use the expansion coefficients to get the original data back. How do I do that? Well, depending on how many of those expansion coefficients I use. If I use a subset, that's the point of dimension reduction. Point of dimension reduction is to use a subset of those eigenvalue and eigenvectors and not all of them. And that's why we had this approximate reconstruction, called that x tilde, which is now U times x hat, this representation that I had, plus adding the mean that I subtracted at the beginning. So I centered the data, mean is linear, I'll just add it together, okay? All right, before I show you an example of how this is used, in the case of, for example, face recognition or many other things, I want to mention that there is an alternative view of PCA, which is not at all, doesn't have a statistical probabilistic formulation. It doesn't have to do with maximizing variance. The deterministic vector space projection, orthogonal projection description, and I want to show you that it essentially gives you the same answer, the two different views. We've had this running theme, looking at a problem deterministically, and then you look at it probabilistically and see if there are any connections. Now, what about this view of PCA? I'll say it in words and I'll show you. So PCA finds the axis which minimizes the sum of squared distances from points to their, and this is the key word, orthogonal projections on that axis. So let's again assume that mu is 0. And what that means, in what I just said in words, if you just write it, it's just, again, we want to minimize. Remember, we were maximizing variance. Now I'm saying that I'm minimizing a quantity. This is a normalization. The sum between xi minus WW transpose is an orthogonal projection. I'll show you pictorially. This is different than the picture that the first day I showed you about the least squares problems, right? This actually, I was asking you, which one is it? Is it in this direction or is it perpendicular to the line? This is the WW transpose is an orthogonal projection. So that's the perpendicular direction from the data point to that vector. And in order to solve this minimization problem, again, we have the same constraint, is we have to use the notion of a Frobenius norm, a matrix norm, which is defined in this fashion. And all it is just basically the trace of A transpose A. So the sum of these A squared elements, AIGs, okay? So where does that come up? I'll just show you this real quick so we can move on to the next topics. So you rewrite the objective function, first of all, by essentially just writing it in terms of, you eliminate the sum. I had a sum in the minimization. I want to eliminate it so I can write it in terms of this Frobenius norm, right? Because that's how I defined, look, that's how I defined the Frobenius norm. So I have a sum and an argument, and I just want to write it in terms of a norm of this form. So all I have to do is just write it in terms of this Frobenius norm. And the next thing that I do is just I write it in terms of the trace of the argument, where this P is essentially an identity minus the product of that orthogonal projector or orthogonal projection operator, W times W transpose. And so I write it as a trace of this product, and just bringing the transpose inside, changing the order, I end up with this expression. And there's a final step, and that final step is that this orthogonal projector operator P has a property that is referred to as idempotent. And what that means is that if you operate P on itself, you still get P. Okay, that's a property of orthogonal projection. And so this P transpose P cancels, and you end up with a trace of this X transpose, which is the covariance times P. Okay. So that is what we want now. We want to next just minimize this quantity. So what I have up here basically becomes the minimizing the trace of the argument sigma times P, just putting P back in here and multiplying, it becomes sigma times I minus sigma times W transpose. Two terms. This is the trace of sigma. This is the trace of the second term, which is sigma W transpose. Okay. Now remember again, I want to minimize this quantity with respect to W. The first term has no W in it, so it's inconsequential. So this is the only term that I want to do anything with. So I want to minimize the negative. That means I want to maximize the positive of that trace of that. And that all that means is essentially you're just expanding the argument in terms of W transpose sigma W. And finally, I did this to show you that, look, this is what we started with when I told you I want to maximize the variance. It's the exact same expression. So regardless of how you formulate the problem, you get the same answer. The answer is essentially you want to do an expansion in the direction of natural bases. By the way, there's another conceptually significant point that's important to be aware of. When we do harmonic analysis, when we take Fourier transforms, we're doing a basis expansion into fixed basis functions, right? Complex exponentials. Here, the difference is that this is what we call a normal basis, because the basis, an adaptive basis, is decided by the data. So that matrix, for each time you do an eigenvalue, eigenvector decomposition, instead of having a fixed rotation, a fixed transformation of your coordinate systems, that new coordinate system is decided by your data. Okay, so that's why it's known as the natural basis. Yes. So that's a good point, but maybe actually just to react to your last statement, maybe it's not easier to solve. Actually, it turns out that it's easier to do an SVD decomposition. Instead of building a covariance and operating on that, I'll show you the equivalence, it's coming up. But it's not about the mean though. It's about the fact that you have the square term. So it's essentially the fact that you have this covariance is X transpose X, right? So you have a square term, and instead of building the covariance and doing the decomposition, eigenvalue, eigenvector, SVD directly gives you that. Okay, I'll show you. That's coming up next. First, I'll show you an example. Well, I think by now we all experience that sometimes airlines don't want to bother scanning your ticket. You know, there's a camera, and if you're legit, you go in. And how do they decide that? What do they do? Have you ever thought about it? Well, without knowing anything about the technology or concepts, ideas behind it, at a minimum, what we know is that it needs to somehow match the image that it just took and compare it with something else. Okay, so what's the most intuitive first idea, the most naive idea is that, well, it will compare it with another image of you that they have, maybe on a passport or something, right? But hard to do that for 100 million people, right? It's hard to do that at the pixel by pixel level. You cannot get a 1024 by 1024 a million comparisons of pixel by pixel of that image with 100 million other images. It's just not feasible, right? So this is an example where dimension reduction has to play a role. So suppose here this picture shows, so we can't do that, right? But in light of what I just explained to you is that ideally we want to find a lower dimensional space in which through this transformation, this quarter transformation, I don't have to do that comparison. I can just do comparison of coefficients, which is much faster, much more efficient. And ideally a small number of coefficients. So how do I do that? Well, here is the example of essentially about, 25 images. But in practice, it could be a database of 100 million images, okay? So you can look at the mean. So this is the mean. You can subtract the mean the way we talked about it. And if you do 25 eigenvectors, this is what you get. And you can see, interestingly, like, for example, what does that mean? Remember, this gives you the direction of highest variance for each pixel compared to the other ones, where you get the highest variance, and then the next direction, and so forth. In this. And it's interesting. You can see which features, in terms of variability, have the highest variance, and then the next, and the next, and then finally, what that is. Some of it has to do with orientation. Some of it has to do with the features. All of that. Okay. But in practice, this is showing it for 25 images. But suppose you have 100 million images. Now, through this transformation, you don't need to keep track of 100 million eigenvectors and 100 million eigenvalues. Because supposedly, because we have captured in successive ways the directions of maximum variance, most of the variability in that original data maybe is captured by 24 vectors, okay? It's an approximation, so you may get only like maybe up to 98, 90% of the variability, but perhaps that's enough for identifying which one it is. So how do you do the search? The way you do the search is you have, let's say, you have just a pattern of eigenvalues. Now I have to compare through a very fast search the eigenvalues of this image that was just taken compared to a database of eigenvalues. How? It's like a least squares fit. Think about that. Let's say 30 eigenvalues, right? You just basically make that comparison, and then you realize that, oh, this is the closest, and then you reconstruct it. Then you can do a comparison with just a reconstruction with a reduced order number of coefficients, expansion coefficients. So that's an example of dimensionality reduction, and of course, it has lots of relevance in many different renditions, and some of it has been alluded to, essentially finding reduced order representations. Okay. And finally, to your point about the connection with SVD. So we don't need, in practice, we don't need to compute covariances and then expand them in this way, compute the covariance and do what I just told you, the eigenvalue, eigenvector decomposition, because really what SVD does, SVD is a generalization of eigenvalue, eigenvector decomposition. In fact, it is a generalization for not necessarily square matrices. We're using it for a square matrix in this case, and that's fine. That's all that means is that we just directly operate on the data vector X. This is the SVD expansion of it, and the matrix of singular values is just the product of these. And the left singular vectors U are needed, as opposed to both U and V. So it's just a more efficient way of computing the same. Okay, I want to transition to the next topic. Are there any questions about what we talked about? Yes. Mm-hmm. the analogy is when you do a harmonic analysis of your data, okay? The low frequency, but larger coefficients, and let's say your Fourier series expansion or Fourier transform, capture more of the lower frequencies, less variations, right? And the higher frequencies are captured with coefficients that reside at higher frequencies, but typically with lower energy. So in this case, basically, when we talk about maximum variance means, well, that's the direction. If you just look at this vector, is where you look at all of the pixels, corresponding pixels, at each, look at one pixel here, and compare it to compute the corresponding variance for each one of them. You end up with a smoother representation because that's what's capturing most of the variability. And the higher frequency information, deviations from that, appear at essentially the final coefficients in the representation. So for example, in SVD and PCA, people refer to it as generalized Fourier coefficients because essentially it captures the notion of a frequency decomposition, but not with a fixed basis, not with the complex exponentials, but with natural basis. Okay, let's talk about clustering for the remainder of the time that we have. Okay, and I want to talk first about an intuitive idea. You know, somebody tells you, come up with an algorithm. Clearly, you have the data, you know that it might reside in multiple clusters. What do I do? And K-means is really probably the most intuitive algorithm for accomplishing that. But it's important to understand how to set up the optimization problem because that has implications about its limitations. So it goes back to your question, you know, how much do we need to know about things that we want to use for essentially an ultimate goal that may not be just doing work in this area? Well, we need to know enough to understand if we are using it correctly or not. Maybe that's the threshold, right? And so that requires understanding the limitations of an approach. That's probably the minimum threshold. Okay, so again, there's a citation here. Here's an example of what's known as semantic segmentation, image segmentation. Of course, you can talk about video segmentations and many other things. And all that means is, Enrico talked about this yesterday, so you have an image and you want to be able to figure out, for example, where is the human, where is the bicycle, and where is the background. In this case, basically, there are 3 clusters. That's the notion of a segmentation. And so what that means is that you have this and you want to be able to break this into clusters, okay? Image. Here's another example, an idea. So if you don't have any labels, sometimes you actually can have, in the previous example, you can actually have some labels. There are many different formulations of these problems. Sometimes you have annotations, you have labels, somebody tells you already what to look for. But if you don't have any labels, then here's an example of an image on the left. And you can just easily just look at it, the histogram of grayscales, right? So for example, you have 256 grayscales. We can talk about color later. And if you look at the histogram, you see that most of the energy is probably centered around very dark and white and some gray in between. That's basically what we're talking about, okay? Now, if you wanted to just cluster by some sort of a thresholding, right, somewhere in here, and then just come up with a binary cluster of these images, basically you would just divide up the histogram and you get the black and the white and you get that information. Now that's okay, but the problem is how do we do it in an automated fashion? Not by just me looking at the histogram and then arbitrarily drawing a line, but is there an automated way of clustering, understanding patterns in your data? And the algorithm, the most intuitive, simplest algorithm is what's referred to as K-means or Lloyd's algorithm. And I'll tell you in words, I'll show you how it's set up. The idea is, you know, so in this case, when we talk about finding patterns, it's the patterns of, you know, not all of your data is distributed everywhere according to some normal distribution, but there are clusters in there. Okay, so you initialize, what does that mean? You pick K random points as cluster centers. Let's call them U sub K. Okay, so the first question, of course, that should cross your mind is that what should that number K be? But let's not worry about that for the moment. Suppose I know that my the data is bimodal, so there are two clusters. I pick k is equal to 2. And then I go through some iterations. So assign data points xi to closest cluster center according to some metric. Let's say Euclidean distance. For each data point, I have two cluster centers. I compare it with this center and the next center. Whichever is shorter, I say that it belongs to this cluster. Very simple. Okay, then update the cluster centers to be the average of its assigned points. So once the assignment is made, then now I know the center and I see what clusters belong to. I take the average of all those clusters and I move that center according to that new average. Now I have a new center. I've adjusted the center. And the stopping criterion is when no points assignments change. You iterate this and nothing changes. Finally, you end up with a frozen representation. So let's look at it pictorially. Here's an example of a clustered data set, right? If I only had one of them, you could say that it looks like a Gaussian, with a Gaussian coming out of the screen, right? Being on top of that, and it disperses. But I have two. You can even think about it, and maybe I should model this as two Gaussians, right? So what's the first step in k-means? The first step is randomly come up with the two cluster centers. These are the two random cluster centers I come up with. The first step in the iteration is find for each one of those points, measure the distance between that every given point between this and that. Whichever is smaller, call that, assign it blue or green. And that's exactly what this one does, okay? So that's the line where the assignments now are made so that these two belong to this cluster, the cluster blue, and this belong to cluster red. But of course, even visually, we know that that's not, the clustering should happen in this direction, not that direction. Okay, so we're not done yet. What's the next thing that you do? For this blue cluster, you find the average location, coordinates, and that average location becomes the new cluster, which is the movement of that x to that point. Okay, same thing with the red. The cluster center moves from where it was to this point. I repeat this now again. I compare the distance to each one of clusters for all the points. I end up with this picture. Okay, and then now again I move the cluster centers. This one comes down a little bit, and this one goes out a little bit. And this is my next picture. I do again point assignments, and I end up with this picture. And if I repeat it enough, after a while, I realize that I'm not changing anything, and that's how you end up with the idea of getting these two clusters separated. That's k-means. It's intuitive, but how do we formulate it? Well, we have to write a cost function, yes? Yes? Depending on initialization. If you change your initial guess, you get, in fact, yeah. So what do you, how do we formulate it? Well, we have to think about we're solving an optimization problem. It's a cost function. What's a cost function? Well, it's what's known as a distortion measure. It's basically, we are minimizing with respect to two steps, right? I already said that in words. First thing we do is we have to make an assignment. For each data point, does it belong to cluster 1 or cluster 2? And that assignment is given by essentially this notion of what's the distance, how do we minimize the distance between a cluster center and a data point? And when that's minimum, we call it that it belongs to an assignment. And then, so over all k's and then over all these. And what that means is essentially we're minimizing with respect to two parameters. One is a cluster center, the other one is an assignment. Does it belong to this cluster or the next one? And R, that assignment that I'm talking about, it's essentially, you can think of it as a vector that has only zeros and ones. If you have only two clusters, it has a 0 for one and then 1 for the other, and then when you change the second cluster, 1 and 0. But in general, you can have k of them where only there's one element 1 in that because of the assignment. Just one of those clusters you make an assignment to for that data point. So you cannot make multiple assignments. For each data point, there's one of those clusters that you're making an assignment to, and that's the role of this R. So what does that mean? Let's look about how we would optimize it. So the cost function, we have this. I already talked about the cluster assignment, and of course the sum over all r's is 1 because it's a vector of all zeros except for 1 for each one of the k's. And the method is known as alternate optimization. First, we optimize for r given mu. That's the first step. You randomly select a mu, a cluster center, and then you minimize r, which means that you decide which cluster that data point belongs to once you have fixed the center of that cluster. So Ri, I've written it as what it is. It is equal to 1. This is how you choose which R, I, K. It's equal to 1. You say that this is the cluster to which the data belongs. If I, for the argument of K, for the cluster index number, that minimizes the difference between X and that center. So the center is fixed. Now I just optimize for which cluster it belongs to. What's the next step? The next step is to optimize for this new center given R. I already know the belongings for each one of the data points, but I want to optimize for mu. How do I do that? Well, I look at the gradient of mu, okay, which is what? This quantity over here. I just basically compute the derivative, and I get this term over here, and I set that to 0. If you set that to 0, do some algebra, just bring it to the other side, you end up with this expression. This is how you decide on mu. What does this tell us? What is it? Yeah, I'm just averaging, computing a new average based on all the data. That's what that is. And I call that the new mu, the new cluster center. Okay, so let me say a few things about the k-means because I want to spend the remainder of the time generalizing the idea that I just told you about. First of all, notice that the fact that what we have this R is what's known as a hard assignment. What that means is exactly what I said in words. Once I decide the distance between a data point and a cluster, all of the centers, there's only 1 in that vector, and all of the other ones are 0, which means that I already say that you belong to this cluster. There's no soft assignment. I can't say that maybe most likely that you belong to this assignment, but it's also possible that you belong to its neighbor with some probability. I haven't done that yet. So essentially, that means that I have a center and no dispersion in my assignment. But ideally, I would want to have that flexibility, and that's what I'm going to do next, which is a Gaussian mixture model. Okay, and I'll show you how the two are. Essentially, this is just a special case of the other one. Okay, maybe we don't need to worry about most of these, but actually for what you're doing, it's important to know that this is sensitive to local optimum. Okay, first of all, local optimum is fine, not global, and you can show that it's guaranteed to converge in a finite number of iterations. And there is a running time iteration that is dominated essentially by the not changing the cluster centers, but the assignment. That's essentially what dominates the computation. So, okay, I already showed this. Let's see. No, I'm going the wrong direction. That's why I already showed this. Okay. Extensions, and this is important because k-means is very sensitive to initialization. That's what we were talking about. And so what do you do about that? I would say the first step, if nobody told you that people have thought about this problem before, you just repeat that for many different initializations and you look what you get. Probably come up with an aggregate. And also it depends on the feature space. It depends on what sort of features you have, and the ideas about kernels I talked about it can actually be incorporated in here. And of course you have to evaluate it, but I can also mention to you that there are variations on that algorithm. There's something called k-means plus, which instead of just initializing in one shot all of the cluster centers randomly, it finds the cluster centers in a sequential way based on some measure. So how does it do that? Randomly choose just one cluster center, not all of them, not all k of them. Pick new center, the next one, the second one, with probability proportional to that xi minus mu k. And so that essentially is the contribution of xi to total error. And you repeat in a sequential way until your initialization of the cluster centers before you start the iteration is done using this method, so that essentially you come up with a better dispersion of that initial randomization. So that's, but the point, the upshot is that as you are going to be playing with clustering with k-means, it's important to understand the role of initialization, because you have an optimization problem that does not have a global minimum. Okay. I won't talk about the different distance measures, how you set up the optimization problem, but I already mentioned that you can use kernels if you have, depending on the feature space for which you're doing the clustering, the data is drawn from. So how do we evaluate these clusters? The generative approach is basically you say how well are points reconstructed from the clusters. That's the notion of distortions. You have the clusters and you want to see how we can generate. It's more generative. The discriminative is that how well do the clusters correspond to labels. You already have the labels. Once you've done your clustering, so that did I get the right labels? And that's the discriminative model is known as purity, is referred to purity. There are many applications, superpixel segmentation. I won't go through the application. Well, I'll show you just one. You have an image. By the way, anybody recognize what this is an image of? Very good, yeah. It's a famous castle in south of Germany, very close to the border with Austria. Okay, so this is the grayscale. And you look at the histogram. This is based on essentially just doing what I just talked about with 2 clusters, 3 clusters. And if you just look at the color space, you get essentially this sort of representation. Okay, you can come up with spatial smoothness, meaning that if you do clustering, sometimes because of the fact that you have this hard assignment, at the edges you may have this jumpy assignments, okay? So there's no smooth clusters that you have, but you can come up with many different approaches to deal with that. For example, you can augment the feature space to contain spatial coordinates, some notion of spatial or local smoothness. That's a variation on that thing. Okay, I'll skip that. The pros are that it's simple, it's intuitive, it's easy to implement. Of course, cons are, and I haven't even talked about that, maybe I will. Maybe somebody will ask me, how do you choose K? It's sensitive to outliers, can get stuck in local minima. And this is the bullet that I want to spend the remaining time, the little time that we have, which is on how to come up with an adaptive cluster centers that don't have the same parameters. Okay, so make it a soft assignment. And it can be slow. And that brings us to the generalization of this idea known as Gaussian mixture models. So what is a Gaussian mixture model? Well, you remember in linear regression, we have a likelihood function where this is the center of our Gaussian. In the generative case, what do we have? We have a parameterized density with respect to the parameters of that Gaussian, mean and variance. And now, given a data set, how to find the parameters? Well, we minimize negative likelihood as we've done all along. And that means we minimize with respect to these parameters, again, making the IID assumption as we've done, negative log of the product of the individual distributions. And you can now, how do you do this? Well, you write the product, you take the log of this expression. Okay, so you have the product of these two. If you take the log of that, you end up with the argument, which is essentially this. Okay, you take the log of that, the first part. So the product becomes the sum, right? And this one corresponds to that. This corresponds to that. You have that many of them, n over 2, and the argument. So you write it in that. So now I have the negative likelihood, or the cross entropy term. And now what I want to do is I want to minimize. So minimize this, exactly the expression that I had over here. And the optimality condition, again, I want to minimize this with respect to these 2 parameters I have. Remember, mean and variance. And by now, you should see the similarity. The mean is the center of the cluster. The variance, we didn't have a variance because it was essentially 0 variance. Either belongs or it doesn't. But now This gives us essentially the notion of a soft assignment. But how do we minimize it? Well, take the partial with respect to the mean, just this expression. The second term doesn't have mu in it. So basically, the partial only involves the first term, and you write it. You set it to 0, and you come up with an expression for mu. The second, sigma appears in both. So you need, it's a little bit, just has these two terms. Okay, once you take the partial, you write it out, chain rule, and then you write an expression for sigma squared. But looking at the expressions, what does this tell us? The most intuitive expected thing, that pick the mu to be the sample average and pick sigma squared to be the sample variance. That's exactly what it's telling us, okay? So obvious, but we can verify. Now, that's just for one single Gaussian, what I showed you. But what if we have two? And if I do the same thing, if this is my data, this is my sample data, and I fit one Gaussian the way I just showed it to you, this is the result of my clustering. That's what I get. That's my fit. And of course, that's far from what we want. What we want is something that looks like this. So how do we generalize that framework to this scenario? Well, in this case, it's just a mixture of two Gaussians. We add two Gaussians. And in general, if you don't know ahead of time how many clusters you have, you need to have k Gaussians, mixtures, and then find essentially now a vector of centers, a vector of variances, and yet one more thing. Any idea what that third parameter is going to come into the picture? Yes. Orientation of what? Well, in this case, I'm showing you this. This is just a 2D example, right? So the Gaussian in this case is just, it's a Gaussian. It's coming straight out of the screen. The dispersion has to do with, dispersion along these two dimensions. But that third one has to do with something you can't see here. Exactly. Repeat that again. Yeah, the relative amplitudes. So I need to have a parameter that captures, it's a mixture. The linear combination, the relative amplitudes. And so what that will give me is the following formulation. I have the conditional probability of the data points, and I have the sigma, I have the mu, I have the sigma mean variance, and something I'll call pi, which essentially has this following constraint. Again, similar to that assignment, the hard assignment, it normalizes, it adds up to 1. We can think of it as a probability. So it's a probabilistic assignment for each one of those clusters. And so I'll just write it now as a Gaussian, similar to before, and the sum of Gaussian. Each one of them is a normal. I'm adding k normals, distributions, and each one of them is weighted so that the sum normalizes to 1. Okay, so back to what we did before, minimize negative log likelihood. Minimize, but now this time with respect to 3 parameters instead of 2. We have pi also, we have to, the assignment, the soft assignment we have to solve for. So that's the negative, similar before, cross entropy, negative log of now, this time this is a multivariate Gaussian, right? Yeah, I have the following sum, so I can essentially, sum of Gaussians. Let me say it correctly. The sum of these Gaussians. Okay, so the first one is the notion of the multivariate, but now I have a sum of these Gaussians, right? So I have 2 sums with a log in between, and I can tell you that there's no closed form solutions. So gradient descent is possible, but there are better ways in terms of convergence and stability to do this, and it's no surprise to you that it will be, goes back to this alternating minimization problem, okay? Nick, can you remind me of where we are on time? We're pretty much done, right? Yeah, so I'll just, I won't go through the details of the derivation, but I'll tell you conceptually what the idea is. The idea, again, by the way, this brings us to the topic of tomorrow, which is generative models, and the notion of latent space, latent variables becomes, it's central to everything that we do there, okay? Conceptually, it means that a high-dimensional data resides in a lower dimensional space, but we don't know. We can't, in order to learn it, we have to introduce a latent space on which we condition. So we solve this conditional probability, and we try to learn that latent space. We have no access to it. In this case, this auxiliary or latent variable, zik, again, it's 0 or 1. It sums up to 1. And for essentially all of marginals for zi, that means probability of zik equal to 1 is equal to pi of k. And you can write its distribution. It being 1 is pi sub k for that k. But the distribution is essentially the product of these geometric random variables, right? Remember, you just multiply them together with the power. Where zi, the vector, has these individual elements, each one of them. Okay, so you can write a conditional. You can condition on this probability of xi on zik being equal to 1. It's a normal distribution, as we have before. You can compute the marginal with respect to all of them. And the marginal is essentially just writing the expression of the marginal. You sum over this latent variable the product of essentially the distribution of that latent variable times the conditional. This is what I was talking about. We don't know the latent variable, but we can write something essentially in terms of the conditional probability for it. Why? Because I already have this. This is the conditional that I have. This is P of Z. I can just expand it. It becomes the sum of the product. And I can simplify it because of the geometric nature of these random variables. And I end up with an expression that essentially gives me a probability that has the pi, the sum of over n Gaussians. And essentially, I have eliminated that auxiliary variable. I can write a posterior and come up with an expression of something that looks similar to that assignment that I had before. But this time, because it's a soft assignment, it's actually referred to as responsibility, which is not a binary assignment, but a relative contribution to each cluster center. And you can plug in. I won't go through the algebra, but you end up with essentially a normalization in the form of the posterior. And the pi, by the way, the term for it is a Gaussian weight, meaning that how much weight each one of the Gaussians has, times the given conditional Gaussian. And finally, the optimization. Now that we have this more general mixture of Gaussians, we can actually come up with a similar way of thinking about the optimization using this alternating minimization formulation. So we want to minimize with respect to these parameters the negative log or the cross entropy term with the following side constraints. Again, this goes back to the notion of a Lagrangian constrained optimization. And in this case, the stationary point is essentially per cluster weight, which is the sum of all of these responsibilities, okay? Per cluster weight, meaning that for each one of the clusters, there is a weight. You can think of it as essentially how much of the tail of that Gaussian is inside that each one of those clusters from all the other ones, okay? That's the way you can visualize it. Okay, so you take the partials with respect to mu, and now this time we have 3, so we have to do that for 3, and this is similar to the previous case. You end up with set that to 0, you end up with a mu that is a normalized version of xi's, but now this responsibility, that term, what a fraction of all of the other contributions comes into the picture when you're adding up, okay? Those, the average, you're computing the sample average. Same thing for the variance. You can go through the algebra, and you end up with the variance to have a very similar structure as before, with the exception of this added notion of essentially partial contribution for each one of those cluster centers. And then finally, the Gaussian weights, these pi sub k's, you can use a Lagrange multiplier and solve for essentially the pi sub k, which again is no surprise that what that comes out to be is n sub k over n. So the relative contribution of those Gaussian weights. It's not a closed form solution. It's not a problem because it already gives us an idea about how we can set up this alternating minimization. And finally, I'll show you this. You initialize 3 parameters, and what's known as the expectation step is that you first compute the responsibility term, which is essentially you already have a pi, you already have a variance or standard deviation and mean, and you draw that from the Gaussian with these parameters with a normalization factor. This is very similar to k-means, where you have a cluster assignment. This time, in terms of a hard assignment, you have a soft relative contribution to one of those clusters for each one. And the M step is now you compute the new mean, the new variance, and also the new Gaussian weight. Okay? And you do it with according to the formula that I just explained. And so you iterate through this until convergence, until assignments don't change essentially. And this is an example of how it works. If you have two clusters, okay, and these are, notice, instead of centers, what do we have now? We have a center, which is at the center of this circle, but we have a dispersion, okay? So that's the notion of a probabilistic assignment. I still have the mean, but I have a variance from the center to this area. So I'm initializing essentially those two. And then I go through the assignment, the steps of expectation maximization. This is the first partition I get, and no, look how it changes. Last time it was just the movement of the center of clusters that changed each time we computed a new average. But now, the parameters of the Gaussian, this is a 2D, right, bivariate Gaussian. So for example, elongation along one vector, depending on, because the variance is now we're talking about the two-dimensional, right? So this is the new Gaussian, this is the new Gaussian, and then you iterate at the next level, it becomes essentially more concentrated. By the time you're at L5, you have these two Gaussians, and then finally you get to this picture, where you have essentially clustered your data according to a mixture of two Gaussians in this example. So what's the upshot? It's similar, in fact, it's a generalization of k-means, where RIKs is an assignment of sample I to cluster K, even though it's a soft assignment. And mu's of the Gaussian, the mean of the Gaussian is the cluster center. And this is the last slide I'll leave with you, because this expression of what the assignment is, if you just look at it in the limiting case and look at its asymptotic behavior, you realize that when as sigma, okay, as this epsilon, which you can think of it as the variance, goes to 0, the dispersion of your Gaussian goes to 0, you essentially end up with the exact same expression as a k-means cost, the hard assignment. So k-means is final upshot. Remember, if you want to do clustering, k-means is a special case of Gaussian mixture model. Gaussian mixture model is one in which, instead of hard assignments, now you have the ability to have the relative contribution of the dispersion rather than just zero variance, which are the cluster centers in k-means. And you can imagine that that has certain advantages. And by the way, even though I went through the steps of how you set up this alternating minimization, you don't need to do that yourself. So if you want to do something for your projects, you can always find code to compute Gaussian mixture models. Okay, I'll stop here and see if there are any questions. There's one here, and then.
One, two. Okay. So how well does Gaussian mixture model handles imbalanced data sets?
Handle what?
Imbalanced data sets. So if we know there is some interesting clusters that we want to figure out, but it's like small amount of points.
Well, the machinery is built in there, right? Because you have this Gaussian weights. So the imbalance, if you're talking about so what are the parameters in terms of imbalance? The amplitude of the Gaussian, that's decided by the Gaussian weights. The spread of the clusters is decided by the Gaussian standard deviation. And the location of where you're focusing on the cluster is the mean of the Gaussian. So the Gaussian weight gives you essentially the machinery for understanding and handling imbalance.
Okay. So if I sort of brute force it with some large amount of Gaussians, at some point I might catch this small cluster that I'm interested in.
Yes, which you're raising a good point, which kind of I alluded to, and I said maybe we'll revisit that during the questions. one thing that I have kind of swept under the rug is, how do we know a priori how many clusters? And any ideas? Again, before I tell you, you could always think about, okay, before I go to the library, I want to think about it. What would I do? Somebody tells you, you have some data, you want to set up this problem. Of course, you have to choose that, right? That's because that's part of the formulation. What would you do?
Will have some expectations of what they are trying to find in this data set.
Yeah. Yes. So you use your a priori knowledge, some prior notion of how many clusters, for example, based on what you understand about the underlying physical principles you would have to have. Enrico talked about this yesterday, by the way. He talked about, I think you talked about the notion of an elbow, right? Yeah. Okay. That's okay. So your answer is that one way is that we already have an a priori information. If we don't, what would you do? Okay. That's right. Hmm? Absolutely. That's one way. I mean, that's a clever way of thinking about how to use the information in your iterations about your fit. But this is no different than what Enrico was talking about, is that so you have to be able to figure out what was the extreme case that you talked about? If you want to fit, if the the number of clusters is the same number of the points, you have no error, right? So that's one extreme. And the other extreme is, overdetermined, underdetermined. It's the same thing. And you can essentially look at the error, and hopefully there will be a transition where you end up with an elbow in that region. You may not always find that. So it's not that it's not guaranteed how that trade-off behaves. But even if you wanted to do something like that, that would imply what's implicit in what we just talked about and what Enrico mentioned yesterday, is that even to generate something that ideally would look like an elbow, that means that you have to sweep through all k. You have to compute. You do have to do this for k equals 1, 2, well, maybe not 1, but start with 2 and go to whatever, and ideally not all the way to the data points, somewhere in between that range, right? Even that is computationally demanding. So there are clever ways of not necessarily just doing this sequentially. We can probably break it down logarithmically so that you can do that in, for example, in a logarithmic fashion, and then look at that, and you can generate essentially insight about how that characteristic changes about that error, that trade-off that exists between overfitting and underfitting. I mean, a lot of these areas have been visited in statistics under many, many different types of problems and questions. There are even textbooks written on topics of what is known as model complexity or model order selection. They appear in many different contexts. If you want to come up with a parametric model, let's say based on a ratio of two polynomials, a rational function, and you want to fit something to it, what's known as an autoregressive moving average model, sure, you can say that my data maybe follows a autoregressive moving average model, but what are the degrees of the numerator and denominator polynomials? And so these kinds of questions have been asked, and there's formalism that you can look up under the typically referred to as model order selection problem. Okay. You have to turn it on. Maybe. No, it's not. The other one was.
Yeah, I don't have a question, but I have a little quiz I wanted to throw to the students so that they can spend their weekend.
Yeah, fun.
While hiking on the mountain and having fun. So the question is, so if you go back, so as Farzad said, this is a generalization of k-means. Now clustering, any given clustering method gives you basically a decision boundary, right? And in the k-means, I mean, the plot that he was showing was very clear. The decision boundary was a plane, a line in 2D. It's a hyperplane in multiple space. So it's linearly divisible between all the, well, if you have multiple cluster, it would be a voxel, but it's always linear, right? In the case of Gaussian mixture model, what is the geometric shape of the decision boundary? Question mark.
Any last questions for Farzad?
So in the beginning of your, I think the beginning 10 or 20 pages, one slide you mentioned that it's not always easy to distinguish between discriminative and generative models. So I was wondering if you can give an example.
Well, it really has to do with how you formulate the problem. So, for example, I mean, it boils down to the fact that you always have a cost function. Okay? You're minimizing some empirical risk. And so that empirical risk is sometimes between a parametric form, like a Gaussian, and another Gaussian with a different set of parameters. That's more closer to a generative. But you could think of it as a discriminative model because you're still minimizing some residual error. Whereas with so it is a discriminative model. That's why I'm using discriminative model and generative model rather than supervised and unsupervised. Because a model is how you are minimizing some residual error. Whereas supervised and unsupervised refers to the type of data you have that you're using. So supervised is the case where you actually have label data. Unsupervised, you don't have label, but there are in-between cases. So for example, there was a discussion we had yesterday. I think somebody asked the question of what do you do if you have, I think it was in the case of maybe the comment you made about Joe Borowski's individual labeling of the data, right? And somebody, you're asking the question about what if the reliability of that data? How do we know we should use all of those labels? So let's generalize it in terms of clearly we can't always rely on the quality of the labeling and the data the same way. So in that case, there is, for example, a formalism where in structured prediction, people talk about the weakly labeled data. Now it becomes somewhere in between. You have data where you know for sure some of the labels are good quality, some other ones are either bad quality or missing. And all of our discussions about introducing this latent space is relevant in structured prediction because essentially what you do is that the ones that you feel are reliable are included. That becomes essentially the supervised component of it. You have a discriminative model. And the ones that are either missing or unreliable, you assume that they belong to a latent space that you don't have directly access to, but then you try to learn. So these formalisms do exist.